more complexity, looking at climate and weather and how it affects these landscapes. Coming up next is Jeremy Freed with Sebastian Busby and Angel Kleck, all with the U.S. Forest Service Pacific Northwest Research Station. They're going to be talking about FIA, and they will tell you what that stands for when they come up here, but remeasurements within the 2020 Labor Day fire and what that has revealed about fire weather effects over forest structure, air associated with mapped burn severity products, and statistical, turn the page, it's a long title, Jeremy, statistical estimates of live to dead carbon pool conversions. So help me welcome Jeremy, everybody.
A long title, but we were trying to be fully descriptive of the content, truth in advertising and all. I'll be presenting the first part of this and then hand it off to Sebastian, sharing our preliminary analysis of the first tranche of post-fire monitoring data from the FIA plot network collected within the 2020 Labor Day fires. Because we haven't yet received funding to support analysis of the data, Sebastian and Angel took time from their funded projects to develop the rapid and preliminary assessment and analysis findings that we'll be sharing with you today. By burning through 261 FIA plots that represent all forests, these fires provide an unparalleled opportunity to learn about Westside Fire. The FIA monitoring network offers a very large and spatially balanced forest sample without regard to owner, forest type, management, and disturbance history. Protocols are largely consistent over space and time. We fully reconcile changes to area and to individual trees. As this map shows, all lands are sampled and plots aren't installed on the non-forest except on national forests. Region 6 uses a spatial intensification except within designated wilderness, which explains the variation in the density of green dots on this map. Owing to their roots in timber inventory, our protocols include lots of measurements on trees, some of which are needed to compute biomass and volume. However, we also collect ecosystem attributes such as on understory vegetation and down wood. We sample larger trees on larger plot sizes so that it's less likely that we'll miss their presence. And the footprint graphic illustrates that plots are sometimes divided into what FIA calls conditions. Those are mapped to account for major differences such as ownership, size class, and forest type within the plot area. These conditions become the analysis unit in our reporting. The FIRS protocol and 44-page field guide supplement have been refined with help from Rocky Mountain Research Station scientist Terry Jane. Sorry about that, I went a little too fast. Over several iterations. We start with the standard FIA remeasurement protocols, then add items that clarify the status of trees and the land that they grew on. For example, is there evidence that the tree was alive immediately before the fire? Another example was there fire suppression activity that could confound the interpretation of attributes that we rely on to understand the impact of fire on soils. We assess the status of tree crowns and of the percent cover of soil surface substrates by char class to derive post-fire indices for these key ecosystem components that describe what the fire left behind. This is not changing very fast. Is it changing? Not yet. All the fires smoldered, as the fire smoldered, we assembled a wonderful group of partners with an interest in this data, a co-production effort that raised just enough funds to accomplish the data collection for the study. By the end of 2 years post-fire, all but 11 plots were successfully visited. The holdouts were typically unreachable owing to hazardous conditions. There were more plots on Region 6 and BLM lands due to the spatial intensification I just mentioned. However, much of the forest land within these 6 fires is private. Most forest areas federally controlled and with older stands common. Privately owned forests have no old forest in this sample. These fires changed how people think about fire in Westside Forest. Was it just because they were large? The Labor Day fires were 25 times larger than the mean annual area burned over the previous quarter century. But size is not the only difference. Comparing the proportion of area at each MTBS rating, it appears that the Labor Day fires had much less area in unburned and low severity and much more in high severity, most likely due to extreme fire weather. We're mostly interested in how forest structure and composition, that is to say fuels, affects fire outcomes, but we can't get to that understanding without accounting for weather. Anyone living in the vicinity of these fires will recall that these fires blew up very suddenly on Labor Day night under an extreme weather event of the hottest, driest, and strongest winds most of us have ever seen in Western Oregon. Daily average, not gust, sustained wind speeds of as high as 26 miles per hour were observed on September 8th. 2 days later, the winds were no longer a factor and fire growth had slowed to a crawl. Knowing the time that fire encountered a plot so that appropriate weather can be linked to it is a lot harder than you might think. We pursued several what ultimately turned out to be dead ends that relied on satellite-based infrared sensors with, unfortunately, temporal or spatial resolution inadequate to the task. Eventually, we found a promising approach. And perimeters of active fires are periodically mapped with airborne infrared to provide operational support for suppression. But the periods are often long. There were only 3 such periods over 82 hours on this fire, shown by the blue lines in the map on the left. These are archived on the National Interagency Fire Center FTP site and inconsistent as to attribution, even as to the time of collection. They are also undocumented, which isn't surprising given that their purpose is to support operational activities, not research or convenience. Given how quickly winds change, this temporal resolution was inadequate to our needs. We divided each perimeter mapping interval, some of which were as long as a day or two, into 4 time periods of equal length. We then took the data from the weather research forecasting model and calculated a mean wind speed and direction over each of those 4 periods. And Angel then used that information to locate a perimeter that was in between the mapped perimeters. In fact, she located 3 of those perimeters to divide up the time between those perimeters into 4 equal time periods. Plots falling between an inner and outer perimeter, whether mapped or interpolated, were assigned a fire arrival time midway between those perimeter timestamps. And finally, hourly modeled weather from the WRF model for that plot location at that assigned time was assigned to the plot for analysis. These in the next few slides show violin plots, basically a combination of mean with confidence intervals, the median, and a frequency distribution. We assessed survival on all trees that were live at the pre-fire FIA visit and immediately before the fire. When the winds exceeded 2.25 meters per second, which is about 5 miles per hour, most stands saw no survival of trees under 10 inches. That's got to be pretty hard on plantations. Larger trees fared better, but under extreme weather, the survival rate, even among the largest trees, was usually under 20%, and most frequently close to 0. With the lightest winds, large tree survival averaged 80%, but even small tree survival approached 50% under those conditions. With extreme winds, the most common outcomes were either very low survival or nearly complete survival, with intermediate levels of mortality less common. Survival did not differ among the 3 wind speed classes that are greater than 2.25 meters per second, so we grouped those as a moderate to strong wind class for the rest of the analysis. Considering all wind speeds, survival in older stands looks to be no better than in young stands. Only under light winds do the results correspond with conventional wisdom. However, older stands aren't statistically different, perhaps because these fires didn't deliver a very large sample of burning under light winds. It was interesting to us that under strong winds, stands 60 to 120 years old achieved greater survival than did stands older than 120 years, based on a fairly large sample. The fire does not see ownership. It only sees the differences in stand structure that different ownerships convey onto the forest landscape by their management choices, including the choice not to manage. At wind speeds above 5 miles per hour, fire is an equal opportunity tree killer. When winds are light, national forests do achieve a greater survival proportion compared to private forests. The sample size on state forests is very small and non-existent for light wind days. Outcomes vary quite a bit and are strongly bimodal within each public ownership. Consistent with what we saw in the stand age graphic, young, even-age stands aren't resistant at any wind speed. Both even-age and uneven-age stands of mid-size and large trees are resistant when winds are light. However, we need to keep in mind that that resistance outcome only applies to the 16% of the forest that burned under light winds in these fires. Even at light winds, the confidence intervals mostly overlap, except that 9 to 20-inch even-age stands do significantly better than those that are less than 9 inches. Because these are FI plots, they can be used with the stratification that's part of the FI design to estimate totals, means, or in this case, carbon density, along with sampling errors, shown in gray, for any desired subpopulation, such as the 2 ownerships and 3 age classes in this simplified table. For young stands, live tree carbon density before the fire did not depend on ownership. However, after the fire, it did. Depending on age class, fire kill rates appeared to be greater on private land, but there's no question that on private lands, a large fraction, more than half, of the fire-killed wood left the forest as salvage in just the first 12 months post-fire. The stories are similar for 60 to 120-year-old stands, though there are much fewer of them on private forest. Which is why the sampling error is identical to the mean. In that case, I think there's only one plot on private forest that had salvage. Essentially, a third of the private forest saw salvage operations in the months after the fire was extinguished, and in most of those operations, all trees were harvested. On national forests, most frequently less than 10% of the carbon was harvested, perhaps because some of those were roadside safety hazard operations, not operations targeted as formal salvage to retain some value and lay the ground for the next stand. And the losses in the older stands on national forests are really pretty staggering. Accepting ODF and its small sample size, the overall pattern is greater retention of live tree carbon on public lands for every age class, at least in the 2 age classes that occur on private lands. Perhaps some trees tagged as salvage dead by crews were live post-fire. It can be very hard to tell looking at a stump as to whether it was live or dead. That could explain some of the lower live tree carbon retention on private lands. Of course, much of what shows as post-fire live on public forests in 2021 is probably not alive today due to delayed mortality, which we just haven't yet assessed. Considering all owners combined, the immediate live carbon retention rate is remarkably consistent across age classes at around 38%. Huge quantities of carbon left the live tree pool on all ownerships as a result of these fires, some becoming immediate emissions, but most converting into the leaky bucket, also known as dead wood. That pool will decay and emit slowly over the coming years and decades unless a reburn happens first. Approximately equivalent climate benefits can be realized from trees that stave off mortality and survive, and those that are salvaged and converted to long-lived wood products or to energy generation if such energy displaces fossil fuel emissions. Let's pessimistically assume that half of the salvaged wood is utilized rather than pile burned or otherwise converted to an emission without energy capture. The fraction of carbon transfers from live to emitting pools is then overwhelmingly dominated by public lands where sizable areas of older stands contain such high carbon densities before these fires. Public lands also contain proportionally less of the young forest that proved not to be fire resistant. Oregon tracks and projects statewide emissions profiles. The goal is to get us on the yellow escalator down to 0. But in 2020, there were still 65 million metric tons of CO2 equivalent in anthropogenic emissions statewide. Compare this to the 70 million metric tons that we estimate left the live tree pool that same year from these fires. Moreover, we track the changes in the down wood, litter, and duff carbon pools between the pre- and post-fire measurements. There were substantial losses, particularly from the duff and litter layers and mostly from federal lands. This translates to an additional 10 million metric tons of CO2e, and in this case, the emissions reached the atmosphere immediately in 2020, not slowly over time as dead wood decays. Keep in mind that this does not count the immediate emissions from combustion of snags and foliage, which we have yet to calculate. In this photo enlargement, you can see what's wrong. These forests don't typically have trees with elevated root crowns and roots running atop the soil. The so-called DBH nails in these trees were 6 to 6.5 feet above the ground, not the 4.5 feet that they were supposed to be. While taking measurements on this plot, Sebastian and I assumed that a thick duff and litter layer would explain this, but no, duff and litter together were only 2.5 inches at the pre-fire visit. This soil likely collapsed by at least 1.5 feet as the fire consumed the organic carbon within. I'd be surprised if those emissions didn't exceed those from the 2.5 inches of duff and litter that went up in smoke. This is not captured in the FI protocol, but we would do well to start assessing soil drop on burn plots by recording the distance from ground to DBH nails. Now I'm going to pass it on to Sebastian.
Thanks, Jeremy. So there's a lot of different post-fire responses we can quantify with FIA data. In addition to mortality and carbon, we can also look at fire impacts to crowns. So to characterize fire impacts to forest canopies and the ecological legacies associated with them, post-fire measurements of forest crown and canopy conditions were classified into a crown PFI, or post-fire index, following a classification system developed by Terry Jane. Crown PFI includes 6 classes and 2 superclasses, moving from crowns that are primarily alive to those that are heavily scorched and reduced to standing bowls, and the superclasses include canopies with live material versus entirely dead material. These classes and superclasses help capture the degree of canopy fuel combustion, and thus what is left to fall to the ground post-fire that influences processes like erosion, fuel and woody debris loading, carbon deposition. When looking at the distribution of crown PFI, we see that nearly all of the forest ends up in the alive crown PFI superclass when winds are light. Under moderate strong winds, nearly half ends up in a dead PFI class, though complete consumption of all foliage is comparatively less common, and that's represented by that transition class. To characterize fire effects to soils, we also borrowed and applied a post-fire soil condition classification system from Terry Jane as well. Soil PFI classes involve thresholds of organic soil cover with a plurality of bare soil char intensity. The first point to characterize here is that pre-fire, 98% of the forest area exhibited organic matter cover greater than 85%. Post-fire, most of the area has shifted to greater than 0 but less than 40% organic matter cover, indicating significant changes to soils from fire effects. Unlike tree mortality and crown PFI responses, wind speed appears to be less influential on the distribution of soil PFI. We see similar distributions under light and stronger winds. Another utility of this data set is empirical validation, which can be used for the evaluation of remotely sensed burn severity products. The Burned Area Evaluation and Recovery Soil Burn Severity Product, or BEAR SBS, is a remotely sensed burn severity product commonly used for evaluation of post-fire soil conditions and thus post-fire management at local watershed and landscape scales. When comparing soil PFI classifications to BEAR SBS classifications, the major takeaway is that BEAR classes track a wide range of observed organic matter cover percent and thus may not track fire effects particularly well. Part of the problem here is that BEAR SBS, like many other burn severity products, is based off of quantifying changes in the spectral signature of vegetation and not necessarily soils themselves. Fire effects to vegetation can be correlated with soils, but not necessarily. We also evaluated how well thematic monitoring trends in burn severity, or MTBS classes, another popular remote sensing burn severity product focusing on quantifying vegetation change, tracked with observed tree mortality seen in FIA plots. We see that while field observed tree mortality falls within sort of the expected ranges we typically associate with low, moderate, and high severity fire, many plots do fall outside of those ranges. This is particularly true for the moderate severity class, where 50% of observations fall outside of the expected range. A large proportion of FIA plots classified as unburned by MTBS also experience low to high levels of tree mortality, which begs the question of whether remote sensing or MTBS data can really determine the presence of fire effects. Analyses and post-fire management actions based off of classified BEAR and MTBS products should be aware that classifications related to fire effects may only be accurate moderately well. These data can also be used to help inform and answer policy and management relevant questions. A hot topic right now with major uncertainty is whether mesic westside forests can be actively managed for greater fire resistance under varying weather conditions. We conducted some preliminary modeling work using machine learning models and FI data to ask if and how forest structure might alter the probability of high severity fire, being defined here as greater than 75% tree mortality volume, while accounting for wind speed and topography. We subset the data specifically to Douglas fir stands less than 120 years old, in other words, stands that are eligible for and likely to actually be actively managed in this landscape. Preliminary models indicate that while wind speed was the most influential factor driving high severity fire, aspects of forest structure were also important, including stand age and forest structure class. Forests younger than 60 years old and the structure classes associated with them exhibited a notably higher probability of high severity fire from those 60 to 120-year-old stands and some of the structure classes associated with them. Further work is needed to tease apart what exactly about these middle-aged stands seems to make them more resistant to high-severity fire under mild to strong winds. And lessons learned could influence the development of silvicultural prescriptions aimed at maximizing stand-level fire resistance. And I'll let Jeremy finish out.
Complaining about network connection. We're really excited about this data. We think they hold tremendous promise for addressing management and policy questions and improving model accuracy. What we shared today is preliminary because the data are not yet even fully in and compiled. For example, full growth, removals, and mortality reconciliation is needed to get the most accurate picture of carbon dynamics. The numbers I shared didn't account, for example, for tree growth between the pre-fire visit and 2020, or for trees that died before the fire. Our summaries don't begin to scratch the surface of what we can learn from a fully funded analysis. Standard FIA remeasurements on these plots are already baked into the FIA budget. They will occur, and as those data continue to roll in, even more questions can be explored. In the last talk today, Ori Chafe will address some of those long-term fire effects questions on the 2002 Biscuit Fire, where this FIRS data was also collected. There's currently no funds to pursue these analysis opportunities, but we hope that that will change. Some of you may decide to help co-produce research with us using these data to address questions that are important to you and that lead to better management options. We welcome your questions. Thanks are due to our co-producers who funded the data collection and for the amazing field and office work that makes this database possible, not just those who collected the FIRS data, but also the FIA crews who collected pre-fire data, the QAs who've worked with us on the protocol over the years, and the information management folks that got the data into usable form for our analysis. Thanks. Sure, that'd be great. Stand up and speak loud, and I will try to repeat your question, or Sebastian will. Why don't you pick someone? I don't have the right glasses on yet.
Yeah, right here.
If there were instances where the remote sensing reflectance data more closely corresponded with fire effects, and did you recognizing patterns in those situations?
Yeah, I mean, can even back up to this slide. Yeah, so the question was, were there circumstances where the remote sensing data actually did match up with the tree mortality that we saw in FIA plots? And was there some nuance there between those relationships? So we can see across these categories, there is quite a bit of agreement. So, for low severity fire, usually we expect less than 25% tree mortality. For moderate severity fire, somewhere between 25 and 75%, and for high severity fire, greater than 75%. And so you can see a lot of the data distribution are in those pools, so we'd say it has moderate agreement with those classes, but then quite a bit of it is outside as well. It's hard for me to tell without digging into the remote sensing data a little bit more and looking at some different measures of spectral signatures or indices to understand why that's happening. So don't have a super good answer to your question, sorry.
Ripe area for research.
Yeah, right here.
I'm wondering about the bear soil burn severity. Were you comparing that to FIA data on soils or tree mortality?
Yeah, so this was actually on FIA data on soil specifically. Given bear is often used to assess soil conditions post-fire specifically, we wanted to match that up with the soil post-fire index we derived from the FIA data. It's hard to necessarily compare the two and say one's right and the other one's wrong, but the general takeaway is that across the different bear classes, we see that there's a wide range of organic matter, percent organic matter cover seen on the FIA plots. For moderate severity fire, for example, we see that there's anywhere from absolutely no percent organic cover to greater than 85%. Way in the back.
Yeah, thanks for the talk. It was awesome. I was curious about the uncertainty of the NPPS similar to the previous question, and whether that changed by structural conditions, and
So the question was, is there a relationship between the MTBS classification accuracy and different structural classes of forests or signatures? That's an awesome area of inquiry, and I think that would be worth looking into to see where, is there specific forest structure stages where classification gets worse, or canopy cover thresholds, things like that. That would be a great opportunity to dig into that further to see, where these products tend to fail the most and where they tend to succeed the most. We need some more effort from folks and funding to do that. So if folks are interested in pursuing that, we'd love to work with you.